33 millisecond period. So it's spinning like 30 times a second, and we're going to listen to it. I saw some people covering their ears, sorry, that's not a very nice sound. You can like just hear you can just make out the 30 millisecond period. So it's spinning 30 times a second. We're going to use even faster spinning pulsars for our gravitational detection experiment. Those are called millisecond pulsars. And these millisecond pulsars are pulsars that have been spun up to very, very, very short periods through accretion of matter from the companion stars. They've accreted angular momentum, they've spun up to really fast periods, like millisecond periods. There's about 500 of these that we know of. And we're going to hear a sound of these millisecond pulsars. They spin so rapidly, you can't make out the individual pulses, you just hear a tone. So you're just going to hear a continuous tone. If you didn't like the previous sound, cover your ears, because this sound is going to be really ugly. Okay. So that pulsar is spinning with a 1.5 millisecond period. It's about 640 hertz. That is the frequency at which it spins, which is an audible sound. That's actually right in our audible frequency range, but it is a very ugly sound. Okay. So why do we like these pulsars? Well, because they spin so precisely, I can tell you exactly what the spin period should be on any day down to very, very, very high precision. So for this particular pulsar, I can tell you the spin period is 4.570136540953. Whoops, 9588 milliseconds, down to that last significant digit. I have a model for this pulsar that is very, very accurate. I can even tell you on May 15th, 2033, when my 12-year-old over there hopefully graduates from college, I can tell you the spin period is going to be this number. And you can see they're very similar. This one is just a little bit longer in this digit, all the way down here. So these pulsars are slowing down with time. The spin periods are increasing, but at a very small rate and at a very predictable rate. And so we can use this to search for perturbations due to these gravitational waves. Here's a movie that shows the super big picture of what our experiment is trying to do. So what you're seeing here are two galaxies. These two galaxies are colliding. These galaxies have black holes, just like our Milky Way, at the centers, right? Really big black holes at the centers of these galaxies. And as the galaxies are colliding, the black holes start orbiting each other and they produce these gravitational waves. These gravitational waves will travel outward through the universe. These galaxies may be very, very far away, like billions of light years away, but the gravitational waves can travel through anything. They can travel through other galaxies, they can travel through empty space, light doesn't bother them, and these gravitational waves will make it all the way to the Milky Way galaxy. And as they pass in between the pulsar and the Earth, what they do in effect is like shift the frequency of the pulsar to either higher or lower frequencies as they pass. Who's heard of a Doppler shift before? You all heard of Doppler shifts? This is like when an ambulance goes by and you hear like, oh, you hear the frequency change as it passes you. This is kind of the same idea. The gravitational waves will make the apparent frequency of the pulsar change. So we can basically listen to these pulsars throughout our galaxy and listen for these perturbations due to gravitational waves. Okay, so I'm going to now tell you specifically about the experiments that I'm a part of and what we do and what we've seen. So I'm part of a group which is called NanoGrav. Scientists love acronyms. If you ever go into science, every project you start, you need to come up with like a really good acronym. NanoGrav stands for the North American Nanohertz Observatory for Gravitational Waves. It's North American because we're a collaboration of astronomers in the United States and Canada. Nanohertz means that we're sensitive to a very low frequency. Nano means 1 part in a billion, so very low frequency gravitational waves. There's about 150 of us or so in the US and Canada. I'm also part of a bigger international collaboration called the International Pulsar Timing Array. And this is a collaboration of NanoGrav and astronomers in Europe, in India, in Australia, and South Africa. It's just recently, they're just in the process of joining this collaboration. And so this International Pulsar Timing Array combines all the data from all these different telescopes all around the world to do this experiment. And it's much more sensitive than NanoGrav itself because everyone in the world is working together, which is always a good thing. So let me tell you a little bit about what NanoGrav does. So we use the very large radio telescopes. We use this Green Bank telescope in West Virginia. Our current data set, I'm going to tell you about, has a lot of data. Oh, it went by so fast, but it'll be on the next slide too. What you just saw flip by before this was the Arecibo Observatory in Puerto Rico. This is a very large array in New Mexico. So we use these large radio telescopes to monitor an array of these pulsars distributed across the sky. We're observing about 70 of these pulsars. We're currently using the Green Bank telescope. This is 100 meters across. I always like to say it's like 3 football fields, but that's American football fields. So I mean, probably like soccer fields. It's probably also about 3 football fields that you would know of, I think. So it's a few athletic fields across. We also use an array of dishes. This is a very large array. And we use a telescope in Canada called the Chime telescope. And we use the FAST telescope in China. We just have a little bit of time on this FAST telescope in China. This telescope is the largest telescope in the world. It is 500 meters in diameter, so absolutely huge. We used to use the Arecibo Observatory in Puerto Rico up until August 2020. When we couldn't use it anymore, this telescope collapsed in December 2020, which was really tragic because it was our most sensitive telescope, and now we can't use it anymore. But it has 57 years of amazing radio astronomy discoveries. So we also work with international colleagues who use telescopes all around the world to do this experiment, and we create data sets, basically like all the pulsar data combined from all these telescopes that we search for gravitational waves in from all of these telescopes worldwide, which is a really exciting project. And you can see some of the telescopes that are used there. The closest ones to you would be the giant meter wave radio telescope in India and this FAST telescope in China. So let me tell you a little bit about how we do our experiment. Like, what do we do when we look at one of these pulsars? How do we tell if a gravitational wave has passed or not? So, and I apologize, the next few slides might be like a little bit more technical. So what we do is something called pulsar timing. We want to time when pulses arrive from some of these cosmic lighthouses. And we can't detect the individual pulses, so when I played you that sound, like boom, 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 you could hear every single pulse very brightly. For most of these pulsars, you actually can't. They're very faint, and they're hidden in a whole bunch of noise. This yellow stuff is just like noise from the sky. And so what we do is we add the pulses on top of all the other pulses. We stack them on top of each other. We call it folding, and we come up with like a very bright, very high signal to noise pulse that we measure maybe over a half an hour. Okay, and then we measure the time that pulse arrived. We said that pulse arrived at 7:20 p.m. on this particular day, and we measure it to 7:20 p.m. and 24.37596 seconds, right? We measure it to very high precision. Then we observe that same pulsar another time, maybe like a month later. We measure another time of arrival a month later. And then we have a model that predicts when that pulse should have arrived. And that model has all this astronomy in it, right? How fast the pulsar is spinning, how fast it's moving, how fast we're moving, all this stuff. And we subtract when the pulse actually arrived and when our best model said it should have arrived, and that is what we call a residual. And if the residual is not zero, that means there's something we're not accounting for in our model, and that may be gravitational waves. You can calculate residuals for everything in life, right? So like, many of you arrived early. If you arrived early, you had a positive residual. Some of you arrived late for the talk, you had a negative residual. If you arrived exactly on time, you had a residual of 0. And so we do this for our pulsars. We just compare when did the pulse arrive and when should it have arrived. And is it different? And if it is different, is that gravitational waves? These models that we make are very complicated, right? Just think about a star in space and all the things that affect when that pulse arrives at Earth, right? So the Earth is going around the sun. That's going to affect the times. As the Earth is moving away from the pulses are going to be getting later and later. As the Earth is moving towards the pulsars are going to be arriving sooner and sooner. Some of the pulsars are in binary systems with other stars. They're orbiting other stars, and that's going to have the same effect. Space isn't empty. The pulses are traveling through gas. That gas delays the pulse, so we need to account for all these different things when we make these models. But this is really exciting because we get to learn a lot about the pulsars and the sun and all sorts of things from these models. And this is the only plot I'm going to show like this, I promise. I know this is like a really boring plot, but I just wanted everyone to see what it is like we are actually looking at as pulsar astronomers, because I know when I was a kid and I imagined what astronomers did, all I thought of was that they looked at beautiful pictures, right? I thought astronomers looked at telescopes, looked through telescopes, they took pictures of beautiful galaxies or nebulae. We never look at a picture when we're pulsar astronomers. We look at data that looks like this. So this is year here, this is 15 years of data, and these are residuals for 3 different pulsars that just show the differences between when pulses should have arrived and when they did. So it's like very statistical. We don't look at pretty pictures, and we're looking for changes in these residuals due to gravitational waves. And you're probably looking at this and you're like, why is she showing us this? This is like so noisy. There's all these points that are higher than 0, there's points that are lower than 0. The different colors are different radio frequencies and telescopes, it doesn't really matter. But the reason I'm showing you it, A, is just to show that astronomers don't all look at pretty pictures. Some of us look at messy data like this that we process with a lot of statistical analysis and math. And to look at the numbers here, so this is this little symbol here, this mu, this means microseconds. So that means 1/1,000,000th of a second. And this means we can model these pulsar arrivals over 15 years to 1/1,000,000th of a second accuracy, which is really pretty cool, right? Like we have really good models. The other reason I'm showing it to you is to show that the models aren't perfect. Like there are some points which lie off the model that aren't 0. So some pulses have arrived late and we don't know why. Is that gravitational waves? We can't tell if we just look at one pulsar. We need to look at all the pulsars and look for a signature among all the pulsars. So let's just step back and ask, like, what would gravitational waves look like in these data? So let's say we have a background of gravitational waves, which is what we think will be the brightest thing for us to detect. And when I say background, I mean a sum of